Okay, welcome back. We're talking about the heap sort on page 98. And so the heap sort is not like a binary search tree, but it is a binary tree. The only rule in the binary tree is that the thing above is larger. It does not mean that the things below it are in particular order. Like if this was a 10, you could have an 8 and a 6, or you could have a 6 and an 8. In other words, the children underneath are not ordered. Okay? You kind of follow me? All right. So let's look at an example here. So here's a heap, and this one's kind of sort of been built for us. Now, in reality, okay, the reality of the thing is it doesn't actually build anything at all. All it does is it kind of sort of looks like this, okay? It looks like this, but in reality, all it's doing is just moving things around in an array. It's not actually building a heap. It's merely ordering things like that. Okay. So you see how the largest one is the top, and then the next one, see, these guys are not ordered, right? And these are not ordered, right? I mean, 5 and 12, right? So each of the children have less, okay? That's the only rule for this heap sort. Okay, kind of makes sense? So whenever there's a choice between the two, I mean, it doesn't really matter if these guys are sorted or not. So you end up with a list that looks like this, and you're thinking, well, how the heck am I going to take that and turn that into a sort? Well, that's how you start the process. So what you do, the first part is you build the heap. Okay, that's kind of sort of what we just did. And then you put the largest value in the next position. And then you just do it over and over and over. In other words, I come across here and I go, okay, 15. Okay, I'm going to put 15 at the top. Boom, boom. Then I'm running along. Ooh, here's a 16. I'll put it at the top. Boom. And so every time you find one, you start putting it at the top, putting it at the top, putting it at the top. You know, start off with, okay, let's. I wish they had a before here. Let's just say that it started out with 8. Yeah, I'll put that at the top. 7, no. 11. Ooh, I'll put that at the top. No. And then it comes back over here. You know, ooh, 12. I'll put that at the top. No. I'll put that at the top. No. Ooh, I'll put that at the top, and then I'll put that at the top. So building the heap is just a mathematical construct, and then all you have to do is just go through and build a heap first, and then just go through and start replacing things at the top. That's how it works. Okay. So the algorithm to do this is not that complex. There's a couple of math errors, so to speak, right in here. So make sure you're looking at the version in supplemental materials when it comes time to implement this. Just saying. Okay. So definitely, what we don't have is what's called a heap fix. This is just the one that kind of sort of puts it in there. The heap fix is what, well, okay. Build the heap, and then this is the fix guy, where I go through and find out, oh, I need to switch things around. Okay. So most obviously, it should be fairly obvious that most of the work is happening in the heap fix guy. So here's the first part where I'm in the construction phase, where I'm going through and I'm building things, the original heap. Okay, that kind of makes sense? All right. So I start and I go, oh, no, 15, okay, great. 3 and 9. You just keep going through it. Kind of stepping back, and then, so this thing works pretty cool. I mean, 8 and it goes down to here, figures it out. 15 goes down to here, goes down to here, goes down to here. So it just walks its way all the way through. Okay. So the worst case scenario, it should be fairly obvious that this guy, the fix heap, is where most of the work happens, right? The fix heap is where things get moved around, okay? That's kind of the idea. So there's 2 parts of this algorithm. The first part is, building the heap, which is kind of like overhead. And then the second part is going through a loop where you're fixing things over and over and over. Okay, so it turns out that this is actually pretty halfway efficient. It actually has a big O notation of n times log n. which in our world, believe it or not, that's pretty doggone good. I mean, I prefer this, but that one has too many headaches. So as a second choice, I'm going for that. And that's pretty good. I'm just going to tell you in advance, that's as good as it's going to get, okay, for the shape of the curve. Now, let's talk about the shape of the curve one more time. If two algorithms, okay, do you remember when we did the insertion sort and the bubble sort? And they were both, okay, they were both O sub n squared, okay? And I said, because they had the same big O notation, they were about similar in computational complexity, okay? Meaning that the shape of the curve was the same. But does that mean that their execution times are going to be the same? Well, no. No, because the insertion sort is a lot faster than the bubble sort. It's just that this is designed to show me in the big picture how it's supposed to grow in size. So what this tells me is, if I had, okay, now again, this is a generalization. Let's say it took 5 milliseconds to do 100. How many milliseconds would it take to do 1,000? Now, you don't normally go to the big O notation to try to estimate the execution time. Not ever, okay, not ever. But in this case, it would give you a ballpark about how long it would take. So I probably shouldn't have told you that, because I don't really want you to use the big O notation to calculate execution time. That is not at all what it was doing. Okay, so I've got some examples here. Here is the log n. Okay, here's plain old n. Here's logs times 2. Log times n, log of n, and then n squared. N squared is like the bubble sort and the insertion sort. Okay, so I'm going to do it like I've always done it. I'm going to grab these guys. And I'm going to go ahead and insert. I'm going to grab me a chart. And I'm going to grab me one of these. Now, it's fairly obvious that the blue guy is really, the n squared guy is really, really just overwhelming the y-axis. So I'm going to take it out and separate it out on a separate chart, because I can't see the curves with that guy in there. So I'm going to do a right click, select data, and just take that guy out temporarily. Okay, now I can see the curves, which is what we're after. I want to be able to see things. So what we want, if at all possible, in fact, I'm going to stretch this guy out a little bit to give it a little bit more room on the y-axis. Okay, so it should be fairly obvious. If you can get a log n, that would be fantastic, because that's just hugging the x-axis. Not practical. An n, like the radix sort, man, that is fantastic. An n squared, okay. An n times log n, that's not bad. I mean, this is probably about what you're going to get in the real world, somewhere in this vicinity of n times log n. Okay? But n squared, man, this guy at this scale would just kind of be almost vertically, it would just go right on up. So, which one of these is the one you're shooting for? Yeah, you're going to need to know a little bit about the big O notation, because if I told you here are two different sort routines with two different big O notations, you're going to have to know, like, a test question would be, put these big O notations in order of complexity. In other words, in order of the shape of the curve, or what the slope of the curve, or perhaps which one has the, in the least complexity, or whatever the right term is. What we're after is which ones hug the x-axis, okay? Which one of these is closest to the x-axis? That would be a good test question. That would tell me that you actually knew what the heck we were talking about when it comes to the big O notation. Okay, now, back to the book. So the worst case scenario is log times n, log n times n. And the best case scenario is log n times n. So wait a minute. Here's a cool trick. If the worst case and the best case are the exact same big O notation, there's no need for me to calculate the average at all, right? Come on. I figured out what the minimum is. I figured out what the maximum is. Those things are the same. So I don't have to do any calculations whatsoever to tell you what the average big O notation is, because if the min and the max are the same, well, then I don't have to do any calculations. Okay. Now, you might just stare at this for just a minute and notice that there's something kind of funky with this guy. And that is, because of the way it's built, okay, this one is fairly immune to the input class. In other words, it doesn't really matter if it's already sorted or if it's a dirty sort or it's got duplicates or, it doesn't seem to really respond to that at all. Now let's go back to this guy. The radix sort. The radix sort is completely immune. I mean, it has no idea what the inputs class is because it's not actually comparing the values. So who cares what they are? This one has some, but not much, dependence. I mean, it might go a little bit faster if these things were like pre-sorted. Okay? So this one is actually pretty good it's fairly immune to changes to the input classes. And you should be able to look at the algorithm, believe it or not. You should be able to look at this and say, yeah, I understand why that's the case. Yeah, you should be able to do that. Okay. I'm ready to move on. On page 106, you talk about the merge sort. Now, the merge sort is a different type of sort. It's what's called a recursive sort, a sort that calls itself. So let me get to that guy. So what we do in a merge sort is you take first of all, we're looking at the example in the book for the algorithm. Let me go ahead and just get to that guy. When you do one of these things, you're going to have to call this thing with n minus 1. The way these things are set up, because it's recursive, first time through it's going to pick like a starting location, and then it's going to get a little smaller one, a little smaller one. So you can't start with n, because in our world, n doesn't exist, right? In an array of 1 to 100, there is no element 100. Okay, so I'm just saying that whenever you call a recursive routine, you're going to have to do an n minus 1. That's just a hint, so when it comes time for you implementing these things, you won't get confused. Okay, so back to the book. So basically what this means is that, first of all, hang on. What does recursive mean? Recursive means that some function calls itself. That's all it means. In other words, this merge example, it's going to call the merge thing over a second time. Now, is that going to cause some space complexity issues? Yeah. I mean, not near as much as the radix sort, because the radix sort was duplicating things on the heap. Okay, again, I haven't sufficiently explained that, but that's okay. And a recursive routine messes with the heap and the stack. So you can't have a recursive routine that runs off forever, infinite loop, because you'll run out of stack. The stack is usually more resilient than the heap, so the stack itself isn't that much of a deal. But yes, there are some issues. So there's two parts to this thing. There's a merge sort, kind of makes sense, and then the merge list. So there's two things like this. So here's how it works. Let's just assume that you had two lists that were already sorted, okay? Let's just assume that. So here's a list of numbers over here, and here's a list of number one, and you wanted to combine these together to produce one list that was sorted. That would be pretty easy, wouldn't it? All you have to do is just kind of keep count of where you are. It'd be like, okay, I'll take the top one here. No, okay, I'll take the top one here. Okay, I'll take this one. Okay, I'll take this one. Okay, I'll take this one. 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 All you have to do is just peel them off the top, because these two lists are already sorted. I just take the lowest and the lowest, the lowest and the lowest, lowest and the lowest, and just go down the list, right? That's actually pretty doggone cool. Well, that's what this guy does. He breaks the list up into smaller chunks, sorts the smaller chunks, and then recombines them together using the simple technique of starting at the top, starting at the top, starting at the second one, third one, fourth one, fourth one. Kind of cool, right? Okay, we're coming up on the 15-minute mark.